Hi, it's a pleasure for me to present joint work with Jean-Baptiste. Hi, it's a pleasure for me to present joint work with Jean-Baptiste Gouray, which is concerned with transfer learning for GANs, or more precisely, Wasserstein GANs. So I will start by recalling you what are feed-forward neural networks, because it would be a good place to start to understand what is transfer learning for these. And then I will introduce you to the object of interest for us, which is GANs. What is the state of the art for transfer for GANs? And then I will introduce our method, which we call Mind2Mind. So all of you certainly knows all the tremendous developments that have been enabled by deep learning. So just a short recall that what is deep learning? It's just basically maps which are compositions of sequences of affine transforms, and the term deep is just saying more than a few. The thing is that affine transformations form a group. So technically, if you compose them, you just get an affine transformation. So there's nothing deep in there. So if you want to have something deep, what you have to do is you have to twist it a little bit by adding nonlinearities in between the layers. So this is an example of a neural network, and the idea is just you feed in some data here, like a vector, and it will output a vector. And so what is the learning part of it? So the point is that when you want to learn, what does it mean to learn is simply to tweak the parameters, so the coefficient of the linear maps, so that when you feed in with something you know, you want the network to output what you know that is in the data, so what we call labels. So here is how you measure this error. So basically, I call this map, underlying map, as a NN, neural network, and it depends on the weights, W here. And then you feed this neural network with some data here. You know what is the ground truth, the label. So you get two vectors, one, the output of the network, and the ground truth. You make the difference, you compute the square norm of it, and this gives you a number. And then you sum on all your data points, and you get a number, which in the end depends only on W. So this is the error of W, and learning simply means you want to find the minimum of this error, and to do so, you're looking for the correct weights. So the main idea behind deep learning is saying, well, if this error is very small on a huge data set, then probably that if I give you new inputs that you've never seen, you would probably make good predictions. So how do you do the learning? It's very simple, because this is just functions which depends on the parameters. So here it's just two parameters, it's just so that we can see it. And basically you start from random place and you gradually look to go lower and lower this error until you reach a minimum, and that's when you have stopped. You have reached your state and you have learned your model. So for that you use gradient descent, and it works pretty well. So it works pretty well. Why? Because this class of functions, so the one which can be encoded by neural networks, is actually dense. So this theorem, you can find it on Wikipedia. So all of these basically goes back to the 80s. So nothing new here. So there's a question is, why is this happening now and not in the 80s? The point is that there's been a revolution which is very similar to the revolution that has happened, for example, for printing. The point is that books existed before Gutenberg, but there you needed a CPU, like a single processing unit, which would make all the computation sequentially, just like this guy who's writing one letter after another one. And then some people realized that, well, we can parallelize all of that using printing machine. And here it's the same. Instead of using CPUs, in 2010, I think some people started to think, oh, maybe we can use GPUs, and because it's just good for matrix multiplication. And actually, it works super well because, for example, here you can see how much time it takes to train a model with the CPU and then with some GPUs, and it's a factor 80 or almost 100. Here it's the same information, but just in terms of speed. So here's the thing. Now it's working. It's working super well because we have tons of data and we have computing power. But the problem is that this has a cost. So the cost is that you use a lot of energy, and that's pretty bad for environment, for example. And now the models are getting so big because we haven't seen the limits of this method. So basically, the more data and the more computing power you get, better results you get. So now it's kind of a race of giants. And that's bad for, first, it consumes a lot of energy. And second, not everyone can take part into this race. So the idea is to recycle things. So basically, if you have spent like weeks of training for a particular model, maybe if you have a data set which is similar, why need to restart from scratch? And that's the idea of transfer learning. So transfer learning here, first there are two main approaches. There's the fine-tune method. So here the idea is saying, okay, I have a new data set. So basically, this is the old energy landscape. Maybe the new one will be very similar. So if I already know the parameters for the minimum of it, if the other one is similar, probably if I start from this place, it would be I will reach much faster, much quickly the new minimum. So, and that's called fine tuning. It's basically just a good initialization of the gradient descent. And then there's a second approach, which is called cut and paste. Here, it's more the idea of hierarchy of features in a neural network. So the idea is the following. The first layers, the one on the left, basically are here to recognize small features like texture or straight lines and stuff like that. And then gradually, as you go up in the network, you start to assemble these features to build meta features, ones which encode a higher level knowledge of the content of the data. And only in the end, basically, you assemble these features and then make your prediction. So the point is that if you have a new data set which basically shares a lot of similarities with the first one, probably you will recognize the same kind of features. You don't need to relearn to detect straight lines or kind of curves and stuff like that. So probably that all the weights you've already learned in orange, you can keep them on the new task. And you basically just need to change your architecture in the higher levels and learn that part. So here's some formalization of what I'm saying here. So this is, if I could see, is from our channel network. And there are two parts, the lower one and the higher one. The lower one is C1, the higher one is C0. And basically, if you have a new data set, you keep C1 and you change C0 to C0 prime. And the thing is that now, since you have C1, which is already learned, you can take the image of your new data set D prime through the C1, and then you will have a high order representation of your new data set. And then you just need to train C0 prime on C1 D prime. And the thing is that then you need to go only once through C1 to define C1 D prime, and then you're good. So this saves a lot of time because you don't have to do backpropagation through the lower layers. So less parameters to train and much less computation to do because you don't need to do backpropagation on half of the network. So that's for transfer learning. Now we want to do transfer learning for GANs. So I have to recall you what is GAN. So GAN stands for Generative Adversarial Network, and basically it's something which helps you to generate. Usually the feed-forward networks are more here to do classification or prediction, but here we want to generate things, so regression of images, for example. So the idea is just to use whatever kind of architecture which can generate some stuff, and then you want to learn to generate this stuff so that it looks like a distribution you have in mind, for example, written digits. And so the thing is that you just need an auxiliary network, which we call a discriminator or a critic, whose job is basically to sort apart between real and fake images. And this is just known territory because classification we know how to do. And basically, then you will use the information given by the discriminator to tune the parameters of the generator until it reaches images that you cannot distinguish from the real training set. And in the meanwhile, the discriminator will try to get more accurate. And in this game, in the end, it will reach an equilibrium, and then you've done your learning. So how to do transfer learning for that? So of course, you can do fine tuning. oh, just one thing I forgot to say, it's pretty efficient. For example, these guys here do not exist. They've been generated, hallucinated by a network. So then what I was saying is that, oh, sorry, I forgot. So here are some math about what I've just said. So what I've described is called min-max GANs. And basically, it's what I told you. So you have the critic here. And the job of the critic is to say positive things about real guys. So you want this to be high when you have a X, which is real. So D will learn to output some high number, and log is increasing, so it's good. While the G here will want to fool it. So basically, when you have an hallucination, you want D to be very small, and therefore this is very high, and therefore this is very high. So if you maximize D and you minimize, so if you maximize through D this number, you will basically be good at discriminating. And if you minimize this around for G, you will be good. G will be good at hallucinating good things. So that's it. Now there's something called, so what I'm saying is that this works pretty well. For example, if you want to do the fine tuning, you see the red one is fine tuned. It learns, it has a very fast, a higher, better result than if you start from scratch. That's what I explained you before. But now the point is that these min-max are not the best GANs. The good ones are the Wasserstein one. So what is Wasserstein GAN? So basically here, Wasserstein distance is just a distance between distributions. And this is an illustration of what would be a geodesic between things. So here you have two geodesics. So it looks very much like the min-max GANs. The only difference is that you get rid of the log. So this is the formula for min-max GAN. And for Wasserstein, as I said, you get rid of the log, and you also get rid of the constant, because if there's no log here, if you do the expectation value of a constant, well, basically it's a constant. So if you want to optimize a constant, you have nothing you can do. So just get rid of that. So now the good thing about this formula here is that this max, just the max part here is actually a distance. This is the Wasserstein distance. So it's exactly the same formula. And then here we can start to understand why this works. The thing is that if you have a real distribution you want to approximate, then if you have a map, let's call it G, then you can push forward a random distribution that I call p-noise. And learning to generate something from the real distribution is basically trying to find the good parameters of this map G, so that these two distribution, the push forward by G and the real distribution, coincide. So here I just rewrite the previous line here, sorry, but replacing P prime by the push forward by G of P noise and P by P real. Okay, and then I take the definition of the push forward. So basically here I just change the distribution from which I sampled. Instead of sampling from the push forward, I sample from P noise, and I'm just rewriting, saying sampling from the push forward is sampling from the original one and take the image by G of the sample. Okay, and here we can see that we basically get this equation here. Or more precisely, to get this expression, we just need to say, now I want to minimize these. I want to find the parameters which minimize this, and then we get exactly what's here. So now you understand what is Wasserstein GAN. So now let's apply. Here is our approach, mind-to-mind for doing the transfer learning. So the idea is simply to factor everything out. So here we factor the generator and the critic, or discriminator if you want, by M. And then we have an hypothesis, which is that the second part of the generator and the first part of the critic, they together form an auto-encoder on M, meaning that if you first encode and then decode, so that's what is written here, you want it to be identity. And why this is good is because if you have that, then to learn a GAN, so to learn G here, you just need to learn G naught to so that it can approximate the push forward by C1 of your data set. So let's say if you have a real data set here that you want to approximate, you push it forward through C1, so you encode all your data, and then you try to optimize G naught so that the push forward by G naught approximate it. And if you have that, then post-compounding G naught by G1 will give you a G, which is actually a pretty good GAN. For example, this is the kind of images we can learn very fast to produce if we have an auto-encoder which is already learned. So here you can see experiments on that. You can see that the vanilla one is just the usual GAN, and we can see that we can get very high accuracy very fast if we do our method starting from different types of autoencoder encoded learned on different data sets. And that's the first part. And then you can also ask, what if we want to compare it just to the fine-tuning? Even if we compare to fine-tuning, it also works pretty well. So now here's what is good about Wasserstein GANs is that we can have estimates and theoretical guarantees on the convergence. So if we make the assumption that we have an auto-encoder, what I'm saying is that the Mind GAN, if the Mind GAN learns well, then the composed GAN, the total GAN is good. That's what I already told you. And the proof is very, very simple. So to say that the total GAN learns well just means that the Wasserstein distance between the push forward of the noise to the real data is small. So if we want to have this small, if we want to control it, we just need to do majoration. I forgot how to say that. So here how it goes. We use the hypothesis that we use the definition of G. So G is G1 composed with G0. And then we use also the fact that the G1 and C1 form an autoencoder, meaning that G1 composed with C1 is identity. So we have this equality here. And then we use a property of Lipschitz function and Wasserstein distance, which says that the distance between the push forward of two distribution by a map is smaller than the Lipschitz constant norm of this map times the original distance between the original distributions. And here we are. Here, if this is small, then this is small. So now the point is that having a good autoencoder is not always easy. And I would say almost impossible to have something really satisfying our assumption here. So we have to relax this assumption. And the idea is to just say, well, we want something, the minimum we can do, or I don't know if it's the minimum or the best, but at least we can work on the domain of the original data set. So what we can assume is that we have done a good training of the autoencoder on the original data set. So which means in our terms that the Wasserstein distance between the true data distribution and the image by the autoencoder of that distribution is small. But the point is that this is a small space compared to the whole space of all possible data, right? So now using that, we can have this following theorem. It says what? It says that the transferred GAN, so G, the new GAN here, is a good approximation of the new data set, meaning that this will be small if all the terms on the right are small. So what does it say? It says that first, the two domains have to be close to one each other. So the two data distribution have to be close. So this distance is small, but also that we have a good autoencoder on the original distribution. So that's our hypothesis here. And we also want that we have done a good job at learning the encoded distribution. C1 sharp of the new distribution is the encoded distribution, and G0 P noise is our mind GAN. So if we do a good job at learning in the mind, and if the two distributions are close enough, and if we have a good autoencoder on the original data set, then we have a good GAN. And the proof is very simple. It's only 4 times, I think, the triangle inequality. So here's the triangle inequality. It says that the distance between A and B is smaller than the distance between A and C and B. And we apply these to what we want to control. So the new distribution and the autoencoder and the GAN, sorry. So here it is. We apply these to C equal the auto-encoder applied to the new distribution. So we get these two terms. And then we want to use the lemma we have already used, because here the point is that G is G1 composed with C0, and here we have G1, so we can see 2 times G1, so we can have this inequality here. Okay, and then we're going to work on this guy here. So we apply once more the triangle inequality. So this guy here is this guy here. So we basically introduce the old distribution in the game. So we had PD, so we have PD here, and we have this term here, which is this term. So we have applied once the triangle inequality. And then we apply a second time this triangle inequality, because here it was PD prime, but here we have PD. So actually we have also added PD here. So we have applied twice. And then we apply once again the lemma with the concerning the Lipschitz constant. So basically here we see G1, C1 twice, so we can apply this lemma. So here it is. And then we're done, because this term here is the same as this term here. So that's one term. We have this term here. That's the second term, which was in the theorem. And that's the third term, which was in the theorem. And we're done. So I think that's about it. Feel free to ask questions.
Well, so thank you for that talk. If there are any questions from the audience, write them in the chat. Otherwise, you can unmute yourself and ask the question. If there are no questions, then I have one. Yael, if you can answer this, maybe. So at some point you need to have an autoencoder, and you assume that this is already trained, but the kind of like the space, the input space for this autoencoder, somehow this is determined by your kind of construction. So I wonder if it's natural to assume that this autoencoder is already there, trained, and if it's already, I mean, if it's ready to be used, or you would need to train it, in which case maybe this would diminish the advantages of your approach.
Sorry, I have some problem here. Maybe it's better if Jean-Baptiste answers. I didn't get completely the answer. You were asking about the fact of whether there was the question about if it depends much on the quality of the encoder. What encoder? What is it? Sorry.
That's great. If you're
excuse me, I have a trouble here. Sorry, now I can hear you. Can you please just ask again the question for a sec?
Yeah, so I was just wondering. Yeah, so it was about the autoencoder, like if it's already trained, and
So yeah, the autoencoder is already trained. That's the whole point of the method. It's to basically leverage on things which are already trained, so we don't have to do it again, and therefore we save a lot of time and energy, basically. Is this your question? Sorry, I'm not sure if I haven't gotten it.
Yeah, for now it's fine. I mean, we can chat offline. That's
okay. Yeah. Thank you. Thank you. Sorry.
I guess we can move on to the next